Welcome to True Projects. In this video, we will explain about surface optimal path planning using an extended Dijkstra algorithm. Introduction. Project examines the use of Dijkstra algorithm in the surface path planning for mobile robots, focusing on scenarios such as untimed terrains, planetary surfaces, and gaming environments. While Dijkstra approach has received a lot of attention, its applicability to surface path planning is still limited. This project presents an extended Dijkstra algorithm designed for determine optimal surface paths. The suggested method models the surface environment using Delaunay triangulation, which converts the triangular mesh into a 2D plane representation while keeping triangular side lengths constant. This change makes it easier to create a two-dimensional navigable surface channel. The shortest ideal route is determined by assessing all viable paths within this channel. The ultimate best path is obtained by converting back to surface coordinates. Coming to objective, the goal of the project is to enhance plan in surface environments by utilizing an expanded Dijkstra algorithm by combining Delaunay triangulation. The proposed approach aiming to improve navigation by splitting the surface into triangles. These triangles allow for extracting path finding by facilitating accurate weight calculations for the expanded Dijkstra algorithm. These are the requirements for execution of the project. In hardware requirements, operating system of Windows, processor of i5 and above, RAM of 4 GB and above, hard disk of 20 GB and above are required. In software requirements, Python IDEAL of 3.7 version is required. These are the design modules for execution. First one is upload dataset. In this module, we will upload the dataset containing information about location and distances. It provides the necessary input data for constructing the graph and performing path planning. Second one is giving source and destination. In this module, we specify the source and destination nodes for which optimal paths need to be determined. It defines the starting and ending point of the path planning process. Third one is generating graph. This module creates a graphical representation of the dataset as a graph illustrating nodes and edges. It offers a visual understanding of the surface environment and the connections between the locations. Fourth one is run traditional Dijkstra algorithm. In this module, we execute the traditional Dijkstra algorithm on the graph to find the shortest path between the specified source and destination. It establishes a baseline for comparison to evaluate the performance of the proposed extended Dijkstra algorithm. Fifth module is run extended Dijkstra algorithm. In this module, we will apply the extended Dijkstra algorithm that integrates Delaunay triangulation to optimize the path planning on the surface. It calculates an optimal path by considering the surface triangular representation and specific conditions. Sixth module is path length comparison. In this module, we compare the lengths of the paths obtained by traditional and extended Dijkstra algorithms. It quantitatively evaluates the performance improvement achieved by the extended algorithm. For execution of the project, first we need to open the code folder. This is the code folder of the project and this is the dataset folder. On this dataset, we will be building the algorithm. And this is the Python main code file of the project. And this is the run.bat file. Instead of executing the project in command line interface, we have created Windows batch file for execution. So we need to double click on it for execution. This is the graphical user interface of the project. With this, we can interact with the program. And this is created by using Dijkstra library in the Python. So first, we need to upload the dataset. For this, click on button Browse. Select the graph dataset and click on Open. Here, it is confirmed that data is loaded. Now we need to enter source and destination location. So I will enter 2 as source and destination as 5. To see the location paths, we need to click on the button Generate Graph. Here, all the circles represents the location and connections between them represents the distance. So close this graph. And now we need to click on the button Run Traditional Dijkstra Algorithm to view the shortest path. Here, the shortest path is 2, 3, 4, 5 and the total length is 11. Now, we need to click on the button Proposed Run Extended Dijkstra Algorithm. So here, the shortest path is 2, 1 and 5 for extended Dijkstra algorithm and this is the length between the 2 and 5. So, among both the algorithms, extended Dijkstra algorithm is showing the least path, which means we need to use the triangular path for reaching the shortest destination. So, click on the button Path Length Comparison for viewing the distance in graphical format. Here on x-axis we have the algorithm names, and on y-axis we have the time length of that particular algorithm, path length. So extended Dijkstra path is shorter than existing Dijkstra path length. So close this graph, close this GUI. Conclusion: the project successfully tackles limitations of classic Dijkstra algorithm-based surface path planning. The suggested method, which incorporates Delaunay triangulation and enhanced Dijkstra algorithm, provides an efficient and accurate solution for optimizing pathways on surfaces. The algorithm's increased path accuracy is enabled by usage of triangles to model the surface geometry and the subsequent determination of appropriate weights. The simulation findings verify its effectiveness and demonstrating improved performance over traditional methods. The contribution of this project, its capacity to deliver dependable and realistic path planning solutions for scenarios requiring optimal surface navigation, providing its promise for real-world application.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.